this slide. Section 11.5, reaction mechanisms. So a mechanism is a series of operations that make something happen, whether it's a mechanical mechanism in a clock, or whether it's a complicated biological mechanism. They're all things that happen in a particular order or a particular way. So our reaction mechanisms in chemistry is a series of elemental steps by which most chemical reactions occur. These are usually going to have an intermediate, so it's a species that's neither a reactant nor a product. You kind of had a hint of that when you were doing Hess's law, and it's like, hey, I've got some combined equations where the product of one thing is a reactant in the other, and so it gets used up. So that would be some sort of intermediate. We're going to break these things down into elementary steps. A reaction whose rate law can be written from its molecularity. And what is its molecularity? It's the number of species that have to collide in order to produce the reaction indicated in a given step. So let's look at our example. We've got some elementary steps in the reaction between nitrogen dioxide and carbon monoxide. If we take our nitrogen dioxide and we react two of these together, right? So in step one, we're taking two nitrogen dioxides and we're going to put them together to form a nitrogen trioxide. And a nitrogen monoxide. Then, in a second step, we can take this nitrogen trioxide and react it with a carbon monoxide to form our product NO2 and CO2. So we're going to form an NO2 and we're going to form a CO2. Right? So that's what's happening. We've got some intermediate. This NO3 over here is made in one step, used up in another step. So it's a product on one side and a reactant on the other. So this NO3 is the intermediate. We have a K1 and a K2 that are going to determine the reaction rates at which each of these two reactions are going to happen. Now, in our elementary step, we're going to define them by the molecularity. That's just the number of things. A unimolecular step involves just one molecule, and those are always going to be first order. A bimolecular step is a reaction involving the collision of two species, and those are going to be second order. A termolecular step is a reaction involving the simultaneous collision of three different things at the same time. So these are very unusual. They're always third order, and they're usually very rare. So if we go back and look at this one, what's happening? This guy is 1, 2. It's bimolecular. This is two things coming together, also bimolecular. So here are some examples. So if I've got A and it's decomposing into a product, that's unimolecular. The rate is always going to be first order. If I've got A plus A or 2A giving me products, that's going to be bimolecular and it's going to be A squared. It's going to be second order. If I have A and B banging into each other, it's also going to be bimolecular, but my rate is going to be K times A to the 1 and B to the 1 because I got 1A and I got 1B. A termolecular relationship, so one where I've got two A's and a B, so 2A and a B. That's going to be Ka squared times B, or three different ones, A and B and C. It's still termolecular, still third order overall, but now it's A to the 1, B to the 1, and C to the 1. Our reaction mechanism is a series of elemental steps that must satisfy two requirements. The sum of the elementary steps have to give you the overall balanced equation for the reaction, and the mechanism must agree with the experimentally determined rate law. So there are lots of ways that you can make these reactions happen on paper. We want some rules to say, well, this is the one that's really happening in the real world. So we want to be able to say, this is the right reaction. These are the right steps that are happening. And so those are our guidelines for which ones are going to be the most valid reaction mechanisms, right? Our elementary steps have to give us the BCE, and our mechanism has to agree with the rate law. If one of those two things doesn't match, we're going to keep looking, right? So let's talk about our rate determining step. Multi-step reactions, like the one that we saw before, have one step that is going to be slower than the others. The reactants can become products only as fast as they can get through that slowest step. It's like the weakest link in a chain, right? Determines the overall strength. Whatever the slow step is going to determine how fast those products get made. If you guys have ever worked in a group project and you've been sitting around waiting for that one dude to finish his part of the product, he is the rate limiting step. Right, so you've got all your things, you're waiting for him, and you're like, oh my gosh, when is it going to get done? That is the rate limiting step. So our overall reaction is only as fast as the slowest step. Everybody else is going to do hurry up and wait. And it's going to determine the rate law and the molecularity of the overall reaction. So here we've got all these cars on the highway. Oh, but there's this merge step, and that's going to be determining what is going to be the overall throughput in terms of how many cars per hour get through on the highway. So in a reaction between nitrogen dioxide and carbon monoxide, we're going to assume that the very first step is rate determining, and then the second step is fast. So we've got reaction number 1, and we're going to say that guy is slow, and number 2 is going to be fast, right? So this guy happens way, way faster. Its bimolecular first step is going to have the following rate law. So the rate of formation of the NO3 is going to be equal to the change in the NO3 concentration with respect to time. So it's going to be K1 times the concentration of NO2 squared, right? Two things in here. It's going to be bimolecular, right? It's going to be second order, because we got two molecules and it's bimolecular. So another reaction mechanism to investigate. We've got this guy, the NO2, reacting with the carbon monoxide to form the NO and the CO2. And our rate that we're going to observe is going to be proportional to the concentration of the NO2 squared, because it's going to be a second overall order rate mechanism. So our NO2 is going to react with another NO2 to form an NO3 and an NO. So our rate is going to be K1 times NO2 squared. That's our slow step. And then we're going to take our NO3, react it with carbon monoxide to give us NO2 back, and carbon dioxide, and we're going to say this is K2, and it's going to be related to the concentration of NO3 and CO. And that's going to be our fast step. The first step is slower than the second step because its activation energy is larger. Right? The first step in this mechanism is going to be the rate determining slowest step. The rate law of the first step is the same as the rate law of the overall reaction. So that first one, this limiting guy, right? Whatever our slow step is, determines our overall rate of reaction. Right? So what do we mean by activation energy? Right? What we have here, this guy, is what's called an energy diagram for this two-step mechanism, where we've got reaction progress, it's kind of an arbitrary axis, and then energy. So we're going to start off with our reactants, right? And then we have to break some bonds, right? As these guys come closer to each other, we're going to need to put some energy into our system. We're going to have these two things bump into each other, right? That's the activation barrier, this EA1. How much energy does it take to form this intermediate? Once they do that, they're going to go down the hill and they're going to form an intermediate, this NO3 and the NO2, right? We then have to pull that apart, so we have a second activation energy, and then they're going to form some products with lower overall energy. So these little activation bumps, these little humps in here, those are our activation barriers. This first one is way bigger than this second one. In order for you to overcome that barrier, you have to roll this ball uphill. And to roll the ball uphill, it's going to take some energy. And at a given temperature, right, that's going to be proportional to your kinetic energy. And just like we saw with intermolecular forces, only some of them are going to meet that threshold energy. That threshold energy for step 1 is relatively high. That's our slow step. It's going to take a while for our very few number of molecules to be able to make it up over that hump. The second one, once they're up here, whoop, whoop, is going to be able to roll down that hill just fine. Right? Our decrease in energy will be sufficient to overcome our second activation barrier. So this right in here, be able to do this, right? Understand these reaction energy diagrams. Since the overall reaction rate can be no faster than the slowest step, our overall rate was just K1, which is our one where we're looking at the NO2s bumping into each other. This rate law agrees with the experimentally determined rate law. And this mechanism satisfies both requirements of the reaction mechanism and is going to be considered a correct mechanism. All right, so let's do a concept check. If I've got a reaction between A and 2B giving me my product C, and I've got the following mechanism, where A plus B is going to give me D as an intermediate, and that happens fast. But then D reacts with B to give me C, and that's a slow step. What is the overall rate law for this mechanism? Pause, go back if you need to figure out what's going on, keeping in mind our two criteria. Okay, so wait for like maybe a couple minutes. I'll pause, and then we'll resume. 3, 2, 1. Our overall rate law is going to be K times A to the first power times B squared. Let's look at another example for reaction mechanisms. Balanced equation for the reaction of the gases nitrogen dioxide and fluoride. You're going to take 2 nitrogen dioxides and 1 fluoride, and you're going to get 2 nitrogen dioxide fluoride gases. And our experimentally determined rate law is first order with respect to nitrogen and first order with respect to fluorine. So we've got 2 proposed steps where we've got K1, that's going to be a slow step, and K2, which will be fast. So our NO reacts with fluoride to give us NO2F and an F over here, right, just by itself. Our fluoride is going to be able to react with another one of these guys that's floating around. And so once we've got this F by itself, it's able to react with an NO2 relatively quickly to give us our product NO2F. Is this an acceptable mechanism? In other words, does it satisfy our 2 requirements? The first requirement is that the sum of the steps should give us the balanced chemical equation. So we ought to be able to add up, reaction A and reaction B and get our overall reaction. So here we're forming this F, the singular F as an intermediate. Right? It's made in A, used up in B. So they will cancel out on either side. And so our overall reaction meets that requirement. Right? So our sum of our 2 reactions matches our overall. The second requirement is that the mechanism must agree with the experimentally determined rate law. Since the proposed mechanism states that the first step is rate determining, then the overall reaction rate must be that of the first step. Right? So this is our assumption, right? So our proposed mechanism says that the first step is slow. Then the overall reaction must be that of the first reaction step. The first step is bimolecular, so our rate law is going to be K1 times the concentration of NO2 to the first power and F2 to the first power. This has the same form as the experimentally determined rate law. And so this proposed mechanism is acceptable because it satisfies both requirements. Right? So it's bimolecular, an NO2 and an F2 come together, our overall